Hello, my name's Adrian Hopgood, and it's a great pleasure to present to you today. I'm Emeritus Professor of Intelligent Systems at the University of Portsmouth. I also act as an independent consultant in the area of AI and its practical applications. Today I'm going to talk about AI in healthcare. I'm going to start by setting a little bit of context specifically about what I mean by AI in the medical domain, and then going to talk about four applications. The first two are to do with predicting patient outcomes. Then there's one to do with diagnosis, and then the fourth and final application is to do with improving the quality of health data, and those data are so important for machine learning applications, and then finish up with some conclusions. So in terms of the context, I just wanted to introduce the idea of these two broad families of AI, which I consider as part of the AI toolkit. In the red circle on the left-hand side, you've got what I've labeled as knowledge-based intelligence. And this is a quite traditional form of AI which aims to capture human expertise and knowledge in a structured, logical fashion, um, sometimes called symbolic AI. In contrast, in the blue circle, we've got data-based AI, dominated by machine learning, and this is a form of AI that's based on spotting patterns in data or finding optimal points in data, essentially using data sets to find information that can then be applied. And I have put some techniques in the middle where they have aspects of both knowledge-based or symbolic AI with data-based or computational AI. I want to draw up some other families as well. The applications we're going to talk about today are what I've described as classic AI. And this is where, like so many systems, these are very narrow in their scope. So they will only, each system I'm going to describe today will just operate in a narrow domain of medicine. And they're also discriminative. That is to say, they are designed to make a decision. That decision might be a classification, a diagnosis, a prediction, that sort of thing. And it contrasts with the emergence of large language models like ChatGPT, which are both broad and generative. So they're broad in the sense that they can be asked any question in any domain, and they're generative in the sense that they generate new information, typically in the form of text, but it could also be in the form of an image or music or anything creative like that. So I said I was going to consider four application areas. I'm going to start with colorectal cancer, informally known as bowel cancer, which is the third most common cancer worldwide and the second most common cause of cancer death, with cases rising as populations age. And each of us has a lifetime risk of 1 in 20 of suffering from colorectal cancer. But the good news is that 90% of cases are cured by surgery. Diagnosis and treatment for colorectal cancer is expensive. So the only published data that I've been able to find was from 2012, which typically quoted 40,000 euros for diagnosis and treatment per patient. I'm guessing that that's more than doubled by now, so looking at roughly 100,000 euros. And hospital care is a major part of that cost. So it'll be really useful for planning purposes to know how long a patient will stay in hospital. So what our model is designed to do is to assist in the guidance for care after colorectal surgery by predicting three key factors. First of all, the length of stay following surgery in hospital, the likelihood of readmission, and the mortality timeline, or more positively, you might think of it as the survival timeline of patients after surgery. Our approach has been that we've used a set of over 4,000 anonymized patient records. These were data that were gathered over 10 years, not specifically for this study, so it's a retrospective study using data that was already gathered. It contains 47 variables. Uh, Most of these are input variables, but some of them are output variables, in other words, describing what happened to the patient after surgery. The first step uh, was to look for any look for the most important variables in predicting each of the parameters we want to forecast. So starting with length of stay, in these bar charts, green is good. It means a short length of stay of 6 days or less. On the other hand, a red bar is bad news. That means a stay in hospital of more than 2 weeks. Um, and this kind of pre-analysis, if you like, enables us to spot a few things. So going through these quickly, um, top left, so having elective rather than emergency surgery is a good thing. Then looking at age, it's good to be young. Looking at ASA grade, which is fitness, it's good to be fit. It's good to have no complications. It's good to have robotic surgery. Uh, the body mass index is less conclusive. And then finally, in the bottom right, it's good to have laparoscopic surgery rather than an open operation. So we did this kind of analysis to identify which were the key variables. And of the 27 input variables, we found that 10 were the key ones for determining length of stay. So we built a predictor using support vector regression. In terms of predicting actual length of stay, it's not that great. So if we look at using all 27 input variables, the root mean square error is fairly large, and it doesn't make much difference if we then focus on the 10 most important input variables. On the other hand, what really matters is whether or not the patient is going to stay for more than 6 days, because that's the kind of cutoff between a straightforward operation and an operation that's more complicated, or a patient recovery that's more complicated. So if we just turn it into that question, then the accuracy is actually pretty good at 83% if we use all input variables, and it doesn't change very much at all if we just focus on the 10 selected input variables, the ones selected as the most important. And that's a key factor, because it does mean that we can actually simplify our models. And if we turn now to readmission, the same sort of process. We start by looking at which are the key parameters in predicting readmission. And it's a similar story. Starting at the top left, you've got it's good to have no previous surgery. It's good to have a short operation. It's good to have elective rather than emergency surgery, etc. And now, as this is a binary prediction, you either are admitted, readmitted, or you are not readmitted to hospital. We can analyze it using the technique known as a ROC curve, or receiver operating characteristic, which is a way of combining the accuracy, specificity, and sensitivity in one graph, where it's good for that curve to be tight to the top left corner. And you can see this one is pretty good match to the top left-hand corner. But if you just want to look at the raw data there, the accuracy, sensitivity, and specificity are all 84% or higher. So that's a pretty good predictor of readmission. And then if we turn to our final parameter that we wish to predict, which is mortality, again, green is good. So green means survival of more than 2 years, which effectively means that the patient has survived the operation. Whereas on the other hand, red is bad. That means that a survival timeline of less than 90 days. And similar to what we've seen before, it's good to have an elective rather than emergency surgery. Again, BMI is a little bit ambiguous. It's good to have zero complications. It's good to be fit. And we've done a very similar analysis, and these are better results still using bidirectional long-term memory model. And this time just focusing on the 91 days mortality. We're now getting, so that's, the patient's in quite severe danger following their operation. We're now getting a very high accuracy, sensitivity, and specificity, all comfortably over 90%. So really good predictor of patient risk there. So why does all this matter? Well, it means better risk stratification, better patient care plans, customized for each individual patient based on their risks, better prioritization of hospital resources, and perhaps most importantly of all, better informed patient consultation so the patients can make the decision that's right for them. And in many cases, if their prognosis is not so good, they may decide not to proceed with the surgery. And this work has been published in the journal Discover Oncology and has attracted quite a lot of press interest. We then moved on to a different problem, but applying very much the same techniques, again to do with predicting patient outcomes. But this is to do with patients who have hemodialysis for treating their kidney condition. And we're aiming to predict a condition known as intradialytic hypotension, IDH, which is a medical episode describing a quite dramatic drop in blood pressure during dialysis. So, as a bit of context, in terms of UK statistics, 3 million people have chronic kidney disease, so that's about 4.5% of the population. And of those, 31,000 people are on hemodialysis using dialysis units. So those people run the risk of IDH, which in its worst case is associated with death, mortality, but also can cause other complications. So as before, we're looking retrospectively at data that has been collected over several years. In fact, we're looking at 73,000 dialysis sessions with nearly 4,000 anonymized patients. Here we have 33 variables, most of them input variables, but some of them output variables again. And again, we've done that analysis to see which variables are most important. And perhaps it's no surprise that the systolic and diastolic blood pressures pre-dialysis and post-dialysis are significant variables. And delta systolic and delta diastolic is the differences before and after dialysis. And what we'd like to do is measure those characteristics before a patient enters dialysis and know what their risk would be. We've used several machine learning algorithms and assessed them using a number of different measures, metrics, the ROC curve, the precision, specificity, sensitivity, accuracy. And there's not a lot to choose between them. They all perform reasonably well. Overall, we found the by LSTM, that's bidirectional long short-term memory, to be a good model, but with the random forest, pretty similar performance too. So looking at the ROC curve and the accuracy, sensitivity, and specificity, using all available data, we're getting figures above 75%. But that's probably an overstatement of the results because it does use measures that are only available after dialysis. So if we just restrict ourselves to the measures that are available as a patient enters dialysis, we get somewhat worse results, but still around the 70% mark, which is still a useful risk indicator. It doesn't have to be a precise predictor in this case. It just has to be an indicator of risk. And this has also attracted us quite a lot of information. We published the results in the Journal of Kidney Care, and it's again been picked up with this press release. And in fact, we've done further work in this domain and have another paper which has been submitted for publication. And this is based on the idea of, rather than looking at that large data set and mining data in it as a kind of flat data set, we're rather than doing that, we're looking at each individual patient and looking at their personal trend through time to see if there's any signature pattern through their dialysis treatments that gives us an early warning that their subsequent dialysis session might be a risky one. I now want to turn to a different application domain, and this is to do with diagnosis in the area of prostate cancer. Prostate cancer is the most common cancer in men, and early detection is crucial. Some of the methods for detecting prostate cancer, first of all, the PSA blood test, that's prostate-specific antigen, and that's I mean, it's a useful indicator, but it does suffer from quite a lot of false positives. And then biopsies are a quite definitive measure of, of prostate cancer, but they can miss a tumour if the biopsy is taken from the wrong location within the prostate. So there is potential for improved diagnostic accuracy through magnetic resonance imaging, MRI. And to show that's how that's currently used in practice, typically a patient will go through a diagnostic workflow where their profile would be assessed. Typically, that will include their personal history and their family history, but also there will be a PSA test. Then they might be referred for an MRI scan if those risk factors are high, and then the MRI scan will flag the risk and location of a possible prostate cancer, and then a biopsy would be taken and then possibly sent for treatment. So we're looking now at improving that MRI scan stage within what we call an end-to-end two-stage segmentation. So segmentation is about identifying the boundaries of characteristics, features in an image. And our two steps that we're referring to, or two stages, are first of all determining the presence of a prostate in an image, and then identifying two particular zones, the transition zone and the peripheral zone of the prostate. And step one, determining the presence of prostate, is really important to essentially save the radiologist's time, because up to 40% of MRI scans taken of a prostate patient do not actually show the prostate. So they're either above or below the prostate. And then even within a scan that includes the prostate, is really helpful to zone in on the prostate itself. And then even more helpful for the radiologist to identify the zones of the prostate, so they can then just focus within that part of the image in identifying any potential cancers. Obviously, a future stage would be to automate the identifying of the cancers, but for now, what we're doing is assisting the radiologists. And the key, as I mentioned, is to highlight and flag these two zones within the prostate. Now, there are thousands, maybe millions of prostate images available for training a machine learning system. Unfortunately, though, they're of little use unless they're labeled. So what we've done is label, using radiologists' expertise, hundreds of MRI scans, just as you see here, where we've drawn out the peripheral zone and the transition zone of layers and layers of prostates for hundreds of patients. And these are the kind of results we get through various machine learning algorithms. Appreciate this is small, so I'll zoom in a bit. So we've got various examples of ground truth here, and various examples of different models of machine learning algorithm for classifying these images of the prostate. And here's an example zooming in on one for what we consider our best model, the multi-rest UNet. And as you can see, there's a pretty close match between the ground truth as marked up by our radiologist and the zones as identified by machine learning algorithm. And we can go further by building this recognition of each layer, each slice of an MRI scan. We can build a 3D visualization to assist the radiologists, where the top of this visualization is the top scan, illustrated to the right, down to the bottom scan, issued here at the bottom right. And we're so building up this 3D model to help them identify exactly what they're looking at within the prostate. So the key findings of this work are that the two-stage end-to-end approach outperformed the other architectures that we tried. It captures the complex anatomical features, and it had higher stability and reliability than other approaches. And within that architecture, we found the multi-res UNet to be the most effective model. And with this approach, we can expect better prostate cancer diagnosis and treatment planning, and indeed a much more rapid throughput from the radiologists. And this work has been published in the the journal International Urology and Nephrology just a few months ago. The final application I want to consider today is about the quality of health data. So we've called this project Healthy Data, Improving Data Integrity for Health Information. So good quality health data has all sorts of benefits, from improved patient outcomes, better clinical practice, better health management, leading to medical innovations and a deeper understanding of disease and treatment. And there are various sources of health data, clinical trials, wearable devices, etc. But we're focusing in this study on electronic health records. Now, those health records can contain errors, and there have been various news stories, some of them somewhat exaggerated, but nevertheless highlighting the risks of errors in data records. And those errors can come from various sources. There can be data entry errors, system errors, processing errors, contextual errors. And we've built a taxonomy to classify those, basically with three broad categories of incomplete data, incorrect data, and inconsistent data. And I'll illustrate that with a few examples. Here we have so-called point anomalies, where the first example here shows a birth date with the year 1690. Well, that's an unfeasible date. It's probably a typo for 1960. On this other column about gender, well, there are 4 valid entries for, you can have M or male for male patients, or F or female for female patients. But here we've got examples of the word masculine, which is wrong. We've got the word female misspelt, and we've got a missing data field. Then we have so-called contextual anomalies, where each field might seem valid in its own right, but there's a mismatch between them. So in this case, we've got an example of the systolic blood pressure is the descriptor, but the code is the wrong code for that, so there's a mismatch. Alternatively, we might have a measurement unit mismatch, where we've got a measurement reading for blood pressure, but the units here are shown as kilograms, which is clearly wrong. And then we can have so-called collective anomalies, where each part of the record appears correct in its own right, but when combined with another part of the record is clearly wrong. So in this context, we've got some male patients, and yet we have a pregnancy diagnosis, which is improbable. So we've built an AI system for checking for these data anomalies and errors. And remember my initial slide where I talked about symbolic AI, logical, knowledge-based AI? Well, we're using that approach to capture expert knowledge from domain experts and existing data quality knowledge. And we're also using explicit knowledge from clinical guidelines and vocabularies. But we're combining that with so-called discovery knowledge, statistical analysis, and machine learning. And that can help us to find outliers, things which are untypical and hence suspicious. And now each of these approaches has its own advantages and disadvantages. So the explicit expert knowledge is available and we have high confidence in it, but on the other hand, it's not easy to scale and it's not easily computable. It is, however, quite explicitly explainable. Discovery, the so-called machine learning or statistical analysis, is easy to scale and it's computable, but it's not very explainable, and sometimes we may have low confidence in it, partly for that reason. So we built a hybrid approach, which builds on the best of each of these to build our model for detecting errors in patient records. And I'll quickly just go through some of the screenshots of the system, highlighting the way that what the tool looks like. You can display patient data, display fields. You can interrogate the fields in different ways and build an analysis. Here's a results dashboard showing that in this case, we've got quite a lot of errors associated with dates, both birth dates and death dates, but also in other fields too. And typically with the dates, they may be invalid or outliers. Outliers are most likely to be picked up through the discovery, the machine learning, the statistical analysis, whereas invalid dates are more likely to be picked up by the explicit knowledge-based expertise. So in conclusion, I hope I've demonstrated that AI has a strong role to play in each of these domains. We've looked at better prediction and planning, better prediction for better planning and intervention in the case of colorectal cancer and intradialytic hypotension, looked at more accurate diagnosis in prostate cancer, looked at health data quality, which is a problem for AI, but I think I've demonstrated that AI can offer a solution. And finally, I want to emphasize that AI is mostly about machine learning with large data sets, but data sets don't always have to be massive. And machine learning is not the only technique that the symbolic knowledge-based AI has a role. Different tasks require different tools. And certainly discriminative and specialist AI remains important despite the world of large language models. Just want to acknowledge the people I've worked with, my colleagues from the University of Portsmouth are in black. So there's an industrial collaborator there, David Prendergast. But in purple, I've highlighted our clinical specialists from the Portsmouth Hospitals University Trust. I want to finish up by just highlighting my book, Intelligent Systems for Engineers and Scientists, a practical guide to artificial intelligence, which has been published in 4 editions now, so I recommend the 4th edition, and it's supported by my website, adrianhopgood.com, where you will find a copy of these slides. Thank you very much for your attention. Thank you, and enjoy the rest of your conference.